I'm John. I'm a neutrino astronomer. If you don't know what neutrinos are, that sounds pretty fanciful, like leprechaun wrangler. If you do know what neutrinos are, it sounds impossible, like alchemist. But neutrinos are real, and neutrino astronomer is a real job. So in between each of those snaps, about 1 trillion, or about 10 to the 12, neutrinos went right through your eyes. How is that possible? So that's the defining thing about a neutrino, is it barely interacts. So you're familiar with light and the photons of light. The photons from that lamp over here can't go through my skin, but neutrinos can go right through. That's the first thing about them. The second thing is they're produced in tremendous numbers in lots of situations, including in our own sun. And that's where most of those trillion neutrinos come from. But the third thing is, how can we know that? How can we detect them at all? How can we know it's a trillion? The answer is, with really huge detectors, neutrinos streaming through them like crazy all the time, very rarely one neutrino will interact. And by counting those numbers, we can figure out the flux of neutrinos from a nearby source like the sun. This is incredibly important for astronomy. The reason it's important for astronomy is because it allows us to see the inside of a thing instead of the outside of a thing. If you go outside and look up at the sun, we're seeing photons from the surface of the sun, which is pretty hot, about 5,500 degrees Celsius. But if you look up with a neutrino detector, we're seeing neutrinos from the core of the sun, and that's 15.7 million degrees Celsius. And what's more, we know that with 1% precision because the neutrino flux is very sensitive to the core temperature. The reason the core is so hot is because of the nuclear reactions that change hydrogen and helium into heavier elements. And that opens the door for why neutrinos are so important in astronomy. It's not just to see into things, but it's to see how those things work. So for example, the stars and supernovae that produce elements and boom and explode and disperse them into the interstellar medium, all of those things, by using neutrinos, we can see their inner workings. So why does this matter for anybody else? Well, with sensitive neutrino detectors, we can do other things. So for example, suppose somebody has a nuclear reactor and you put a neutrino detector next door. You can tell if the nuclear reactor is on or off, and you can tell if it's producing plutonium or not. But even if you don't care about those practical things, neutrinos are just interesting. So if you look around us, the elements that make up the Earth, like iron and silicon, those were made in stars and dispersed by supernovae. Many of the elements necessary for life, carbon and oxygen, similar story. And all of those elements, as those elements were created, they were accompanied by neutrino emission. So by measuring all of the neutrinos from the cosmos, we're measuring something about the history of the formation of all the chemical elements beyond hydrogen and helium that were made in the Big Bang. So we're surrounded by neutrinos. Many of them are coming from the cosmos. My job is to find them out. And if you see one, let me know. Thanks.